introduce you to Professor Ekmel Özbay. He happens to be my classmate from this department. We both graduated in 1987. He always was beating me in the exams, except one exam. And then in that one exam, he used to say that. I'm still saying that. My friends were very proud. So, you know, he was excellent as a student also, and he had a double major here, not only electrical engineering but also physics department he graduated from. And then he went to Stanford University for his master's, PhD, and then postdoc studies, and then he worked in the United States for a short while in the university, Iowa. And then, I guess 1 year before me, he came back to Turkey in '94, and then I came to Turkey in '95. He went to Bilkent University in the physics department. I was almost going to go there, but I preferred to come to electrical engineering at MTT. So he's doing excellent research, but not only that, he's developing some technologies, critical technologies for Turkish industry also, and then he is also the CEO of a company, a joint company established by Bilkent and Aselsan. So I'm happy to let him give you an excellent presentation that I know he will be.
So I have to thank my friend, a long-time friend. We have known each other since 1983, so it's more than 35, 36 years now. So it's always a pleasure, you know, to come here back to home. I hope this department is home, because this is, I think, where I really started learning the basics. You know, of course, in high school you get something, but it is the university education that puts your goal, I mean, long-term goal. And I'm also a very proud member of to be an alumni of this department. So today, I have different hats. I will try to put the first hat because I also like to be a role model in that sense, that an academician turned into, I would say, a CEO. So I will give you the story of how we came to that point and our experience with it. I'm also the director. Actually, it's kind of combined. What happens is we develop the technology in the research center, but transfer it to the company. So I will try. So it is in a way a spin-off company. So let's start with what is a universal spin-off company. That's the definition. I will say textbook definition. So these are companies created for the exploitation of products or services that are developed using knowledge of technologies created by academic research. So you do research in a university, and you see that you develop a technology, let's say, but the technology, of course, has to have, you can develop the technology, but there are other important things or elements that to be successful. So just developing technology is not enough. So what are the essentials? What is needed to start a spin-off company? So first you have to have enough number of personnel. So you have to have an educated personnel. So being in a university is quite helpful with that one. And I will go through all of these. You have to have the knowledge and technology developed by the people. But developing or having a successful project is not enough. What you develop has to be feasible. Which means that if you want to put it into a product, return to a product, you have to spend some money and you have to recoup the money. You get the money back, which means that to get the company going, what you should put in should come back, which is called feasibility. So you have to generate enough profit so that you can pay for the expenses. And of course, still, you have to find the money too. So that's, for instance, one of the big problems that still Typhoon faces. I will tell you my solution, because especially if you are talking about millions of dollars, personal income or personal investment is not enough. You have to find someone else to pay for this. So let's start with the people. We had a summer party. So not everyone was there, but we are now close to actually more than 100 people. I will tell about them later. But in the meantime, I should say that we had a lot of very, I would say, high quality graduates. So these are my PhD students who finished their PhDs with more than 15 science citation papers. Again, I do not need that list because I had only 5 papers when I finished my PhD in Stanford. But I had very good students, and thanks to them, we have a lot of publications. But if you look for who is right now in Nanotam and the company, the first one is the Nanotam, second one is the company. We are now almost the same size in both of them. But typically we transfer people from the center to the company as we develop new technology, and I will give examples. So we are around 110. Most of them are research engineers, and these research engineers are actually working on their masters or PhD in different places in Ankara. Some in Bilkent, some in Medreş Technical University, mostly in Hacettepe, because Hacettepe is a very strong applied physics department, also in Ankara, Gazi, Top, etc. We also have principal investigators, 10 of them, but these numbers will increase as some of the research engineers receive their PhD. We had training technicians now. The number had increased because we are into production in some of the technologies. And also, I keep, I would say, research group that I still publish. We also have project management, quality management, human resources, etc. So it is now, we have a lot of people. So besides the people, you have to have the knowledge and the technology. I already showed the success of my students. Thanks to them, we have been publishing quite a lot in the past few years, I would say, in the past 10 years. So our publication number is now close to 500 citations. And actually, all of them are from Bilkent, by the way. So this is since I returned back. Now, you may see a dip here. We typically publish around 30 papers. This is the dip where I became CEO. So I have spent a lot of time with the company, so I didn't spend time for research. But now we are back to, I think this year we will finish maybe around 40 papers. Why I'm showing this? I'm showing that we had good science, I mean excellence in science, and we are actually, it has to be together. You have to have, if you cut the science and just work on, say, application, after a while you lose your edge. So we try to keep our edge in that sense. But of course, just number of papers is not enough. The quality, there's a lot of way to measure quality, but the easiest one is to take the citations. So our citation count is now more than 17,000, H index is 58. So we are getting around more than 1,000 citations per year, and this is only 5% self-citation. So most of we are representing both Bilkent and Turkey in that sense. Another, again, I'm showing this to show that we are still excellent in science. Speaking of science, as you know, Science Journal is maybe the top journal in the world in terms of reputation. So the only invited paper from our country was published in 2006 from our group. And since then, we had more than 3,000 citations, making the most cited paper ever published from Turkey. And this will still be for a long time because the paper that follows, other Turkish paper that follows this is almost half of it. So this is the most cited paper in Turkish, modern Turkish history, I would say. And this became now, we were predicting that plasmonics will become a huge topic at the time, and most of our predictions actually came out with the truth. In the meantime, we were also very active in patents to develop the technology. We have now more than 62, I think, applications, and 15 of them has been granted, the others are still in the process. And this is how it changes in here. In 2019, we had around 20 applications. So in a way, we are doing good science, but also generating enough technology to put into products. So we have been working on gallium nitride, let's go to gallium nitride for some time. Actually, for time, I'm talking about 15 years, because it takes a lot of years to develop the technology and eventually to go live. Why gallium nitride transistor? Because gallium nitride has the semiconductor. It has a very wide band gap. It's 3.6 electron volt. it has a high electron velocity, saturation velocity, which means that we can also make it a heterojunction. So you can confine electrons in a two-dimensional structure, in a quantum lab. And in turn, you get very high electron densities. So you have the high voltage saturation, high electron, which means that you can get high current. But wide bandgap also means that you have a high breakdown, critical breakdown electric field, which in turn becomes high breakdown voltage. So all of these properties, as you know from your electronics courses, is suitable for high power transistor. To give you an example, the amount of microwave power that you obtain per millimeter of gate is about 10 to 20 times more than gallium arsenide. How is this possible? Because it also can handle very high temperature. Because we are processing S bands, we are generating around 10 watt per millimeter with 60% efficiency, so we are generating 5 watt per millimeter, which means that the temperature, the junction temperature is around 240 Celsius. Gallium nitride can handle this temperature, but gallium arsenide silicon can never reach those temperatures. So I would say this physical properties makes it the king of transistors for gallium nitride. So that's the reason why we started working on this technology. So it's actually, these are kind of baby steps. We first developed, I would say, simple structures, just transistors, and look for their performance. We purchased an MOCD system to grow the material, so we are also growing the material. That was a R&D scale machine. Actually, that was purchased in 2004. Now, we still use it, but we have better systems, as you will see. We had the equipment to process these transistors, and also the facilities. So these were when we were doing these activities in the Center Marathon, and we were able to get a gallium nitride based high power amplifier against a MIMIC design. We grow the material, we do the fabrication, we do our own modeling, so we have a PDK for the structure, and then we design our MIMICs. So that was a 21 gigahertz amplifier with a 1 watt output that was used for a satellite application. So it was, again, was a project. It's called, it was a functional HF transponder, and we successfully tested it in the module developed by Aselsan. So we had generated now-gen technology, but how about the market? Is there a market to actually put turn this into a product? Actually, gallium nitride has a lot of application. Besides the defense application, like in the radar or the electronic warfare application, there is a quite application in high power electronics. I will be talking about them. Because if you use gallium nitride as a switching, in switching power supplies, you can get more efficiency than the silicon counterparts. You can also use them in space because they have a tolerance for radiation. They are radiation resistant. And for the upcoming 5G and 6G telecommunication, especially their efficiency, makes them ideal for the base stations and also WiMAX, etc. Actually now, you are using LED in gallium nitride every day. All the LEDs, I'm talking about white LEDs that are currently in market, actually uses gallium nitride technology. But this is kind of, we missed the train in a way because this became a commodity, and the price has dropped so that there is no way to make money in LED business if you cannot find a niche application. So this is how the gallium nitride world market will develop in the coming years. Again, RF is about 1/3, opto semiconductors is another third, and power semiconductors is another third. And now the question is, are we going to be a consumer or a producer for this market? We say that we want to be the producer, just not the consumer. So this is how we expect the GaN device market size is changing in the coming years. And in terms of Turkish market, Çaflat was one of the projects that Aselsan was interested. So this is, I will be talking about a little bit more later. This is the radar for systems. So Turkey will build actually 4 ships that will be placed in our seas, mostly on the Aegean Sea. And these radars will have a phase array, these ships will have a phase array radar that will have a peak power of 80 kilowatt, and there will be 54,000 active elements, so it's a phase array system. So you are talking about hundred thousands of limits. So we made a basic feasibility analysis and say that if you look for the upcoming projects that Aselsan is planning to have, like this, and along with the other electronic warfare projects, we may have enough market at least to get the company going. So, which means that you have to now look for the financial sources of investment. Who will pay for this? So what we did was we had an agreement with Aselsan. I went to the university president, Professor Atarak, who is a member of, who's an alumni of this department, and he said that, okay, we are in. I agree to pay half of whatever it costs. So Aselsan and Bilkent signed an agreement at the time, and we had a company 50% owned by Bilkent University, 50% owned by Aselsan. In a way, we were bringing the technology and Aselsan is bringing the market, so it was a nice combination in that sense. So October 14, November 14, so about 5 years ago, we formed the company. This is the Sicil Gazetesi. Basically tells that companies own half of that part. Now, most of these companies are typically 51-49, but we wanted 50-50, so it has to be always unanimous voting. And we never had a problem because university and Aselsan has different goals, so they don't compete. They actually, they are very happy to work with each other. University is proud that it can show that the research in university is now becoming a technology and product, so it is a showcase for university. For Aselsan, it is getting both technology and also very critical components, which I will be talking about. Especially nowadays, we are very, afraid that America will put these sanctions on us. Sanctions means that you cannot buy anything from America, mostly from the Western countries. Or if you do a business with anyone, if anyone does business with us, America will put sanctions on them, so it will kill the economy. But more importantly, we will not be able to buy the critical components. So Aselsan is now, I will show you other things. Along with Tayfun Hoca, we are providing all the essential components, critical components that Aselsan has a hard time to get from outside. So this was how we formed the company. I'm not a rookie anymore, it's been 5 years, but it was quite an experience. How about the investment? We plan to have a $30 million investment. That's where you need a backing of a large entities like the university. Bilkent University, we should say maybe Bilkent Holding, because they are inside within each other. Bilkent University had 40 companies, ours was the 41st company, with an annual sales of $2 billion. So university has enough money to back up us, which means that we can get credit from the banks. Same thing for Aselsan. So each of university put $3 million, Aselsan put $3 million, that became the capital. You have to get capital from the investors. And then we applied for a credit of $24 million to the banks. We showed the feasibility to them and they liked it. Actually, there were 5 banks who agreed to fund us. So we had to have a small competition between them to get the best rate. We were able to get the 2 plus the bank, it is called this London Exchange something, I forget the prime. Libor, yes. Libor plus 2, so we were able to get like 4%, which was quite good at the time. Now Libor is around 5, I think, so, but we were able to get it at 4%, very, very good. And we actually are now in the paying phase. So we get it, we use the whole credit, and now we are paying it back. How did we spend the money? Out of 6 million, we spent mostly on the, I would say, for the building and clean room. And also we spend for the epitaxy system, for the micro-nano fabrication facility, along with the characterization. So I will show some picture. I will talk about where the money came from. So this was the groundbreaking ceremony. Some of the, I would say, people are still, are present there, but most of them retired or they are not there. The minister, I think he's not a minister anymore, he was the education minister for a while. Said, we used to call it undersecretary, not the presidency. He's still, Ismail is there. So this is the building. It was 4,000 square meter, the company building, and we had around 700 square meter of 7 clean rooms in there. So this is the organization. I'm the CEO. We have one person from Aselsan who joined us as the genel müdürlüğü, vice, I say vice, actually he's the CFO in a way. And we have 2 directorates, one for the gallium nitride RF, and I will talk about one for the photonic technologies, along with other entities. In the meantime, we keep the nanotam for upcoming technologies, and also we do basic research along with some administrative people. So I will be talking about what we do for gallium nitride RF technologies, especially in the company. So I already talked about why this material is good, because it can handle very high powers. Actually, Nobel Prize in 2014 has been awarded to people, Japanese scientists who developed gallium nitride materials used in there. I always show this. So this is the first, I would say, order we have got into the company. We are developing, we already developed the for S-band technology. We also work on Chaflat. I already mentioned about this. But besides the Chaflat, there is also another X-band application, which is called Nation Fighter Project, MMU, Ünvan Uçak in Turkish. So we are developing a special gallium nitride unit that has 3 different functions on them. So how do we do these technologies, or how do we develop these chips? We start from the MOCVD. MOCVD means metal organic chemical vapor deposition group. So what you have is, you have metal organic gases, and you combine them on a very hot silicon carbide vapor, and you grow the material, gallium nitride material on top of it. So this shows what we have in this group. We have MOCVD facilities, but we also have a lot of epi characterization facilities. So this was our first system. This is the second system, which costs around 2 million euro to put together. So it's an external system. We can grow up to 7 2-inch or 3-inch wafer. Once we grow the wafer, we characterize them using our facilities. This shows our X-ray, XRD system. So all of the wafers has to be characterized and go through the quality control processes. So if they pass it, they are delivered to the fabrication. So this is the photoluminescence method, where we check the uniformity of the wafer, both in terms of composition and in terms of thickness. We also check the electrical parameters. We typically have a 2-dimensional electron gas, so we have to make sure that it has the same, I would say, NS, which is the sheet charge density, mobility, and also sheet resistance. We make like 800 contact measurements to get that. I will show you maps for that. So these are the typical results. This is obtained from the photoluminescence measurement. Notice that we look for the aluminum composition using this. And using the contactless hole measurement system, we are looking for the average value for the sheet resistance, sheet density, and also mobility. And we check for the uniformity. And these are quite good numbers for gallium nitride MOCVD wafers. About fabrication, we also have a big team in there. We had the patterning, basically lithography and e-beam lithography. We had the substrate process, basically plasma properties, and then we had the additive processes, which is the PVD and CVD, and also we have the organization. Some pictures from the clean rooms, which shows the, this is the yellow room where we have the optical lithography. We have a substantial investment for making PCM, process control monitoring. This is the entrance, again, it's another part of the clean room. We have about 13 major steps, 124 different steps. So it takes around 130 hours to finish one process. We typically work from 8 to 12 all day, so it's double shift, and 6 days a week. So with this process, we can finish one wafer, I mean, from start to end, around, I would say, 10 work days, so it's almost 2 weeks. And we are, nowadays we are starting one process every other day. So we are almost in production, but we also have 40 people working for that system to be functioning. So this shows some pictures from our steps. I mean, the most critical step is the gate. That's why we have this expensive electron beam pattern generator. We use electron beam lithography to define our transistors. We don't have a stepper. We are not rich enough to have a stepper. But to get these, I would say, different shapes and 0.1 micron gates at least, we need electron beam lithography. Notice that this is, for instance, this is where the touches the I would say semiconductor, so this is the gate. But we also have these feed plates to get higher breakdown voltages. So we will actually we do simulations, all of these, etc. We use Silvaco for the simulations, design our transistors, I mean high power RF transistors, and then try to generate the same pattern in using our electron beam lithography. So besides the front surface, we also have a back surface in which we open up these wire holes. So we grind it down, these typically start around 400 micron thickness, grind it down to 100 micron, and then put a wire hole and of course electroplate it so that we can have a microstrip technology. So these are some of the finished structure. This is an S-band voltage amplifier. This is an S-band transistors. Again, some S-band transistors, and this is an X-band power amplifier. Some other pictures from, we use these inductors, capacitors. So we have, of course, we have to model all of them one by one to come up with a good electrical model. Some of the equipment we use for optical, we use the Carl's master liner. We have a couple of them, and we also have the Heidelberg exposure tool. We use it for laser lithography, but mostly we are using this to write our photomasks. This shows some of the PVD equipment we have. We currently have two E-beam deposition systems, one sputter system, another PVD is on the way. It will be delivered next month. And we also have one, this is Turkish Nanolab, it's called PIMS. It is a sputter system with high for different application. This is our PCB system from, actually we have now two PCB, one from Santec, one from Samco, Germany and Japan. So some pictures from there. And some of these are the other plasma systems. We have 3 ICP array because we needed 3 different steps. So all the steps have their own equipment, etc. This is the most expensive equipment we have, 2.3 million euro. It is produced in Poland, in Netherlands, local. Currently it's owned by a German company, right? But it used to be owned by an American company, but it is manufactured, designed and manufactured actually in Netherlands. Go back. So we also have you cannot use the previous equipment for imaging, so we have to purchase other SEM along with our previous E-line. So we use them to check our gates. We measure the physical length of every gate that we produce, so as a part of our PCM. for backside, we have another room. We have one grinder, 2 dicers, along with some other equipment for packaging. So grinder, dicer, mounter, UV curing, debonder, die handler, all of these are in a separate room for back-end process. So what do we do with all these instruments? We work on S-band, X-band, K-band, and double band. We work all of these bands actually, along with measuring capability. So these are the applications that we are currently working on. We work on M5 switches and low-noise amplifier. For S-band, as I told you, we are developing the transistors. Aselsan wanted us to develop transistors. So each power bank is around 20 watt, and when you combine 4 of them, you get 75 watt with an efficiency of 65% and the power density around 80.5